Thank you very much, Paul, for this excellent presentation. We will go on with all the presentations and have Q&A at the end of our session. Please welcome our second speaker, Professor Hans-Ulrich Kautscher from Heidelberg, Germany.
Thank you, Michael. And we enjoyed a wonderful presentation on neuroradiology. And the good message is I will be talking about a different topic. There won't be any overlap between these two presentations. And what we have already heard in session 1 this afternoon is that computer analysis of radiologic images and chest images is nothing new. Already in 1963, people tried to segment tumors, effusions on chest X-rays. And we have been pursuing this for a long time, and it was almost undetected by the majority of radiologists, and also only in the last year is the big development coming, powered by the increase in nowadays we have the hardware and software to really address the issues because they are complex. And now we are moving from simple segmentation of findings to characterization and then to the learning algorithm that will help us to really detect and see that sensitivity and specificity of these software tools are in the same range as of an experienced radiologist. And we can then move the target and say, okay, we want to go for tuberculosis on chest X-ray. And you see that in this approach, they are looking and trying to create these heat maps to demonstrate and to visualize the abnormality. And then they nicely mapped out that when you are using this tool, you can increase your performance with regard to sensitivity and specificity in detecting tuberculosis on a chest X-ray. And this is very new work just published this week in European Radiology, where the Korean group, they are aiming at pneumothorax after intervention, after CT-guided biopsies, for example, and you see that they are indicating where the problem is, and again, their results are very, very good. They will see that they have a pneumothorax internal validation this year is sensitivity about 90%, specificity about 96%. So this is something that can really be used as a concurrent reader or as a pre-read, which can then be used also to increase, to prioritize your work list. But certainly addressing one issue like nodules, tuberculosis, pneumothorax is only a very minor approach. What we actually will need is a program that will prepare the reading of a chest X-ray in a comprehensive way. So to classify the chest X-ray as being normal, as having an effusion, a cardiomegaly, consolidations, edema, or pneumothorax. And there are first tools out there who will actually analyze multiple abnormalities. And then you can see here these are all the different findings, and these are the specificities. And not surprisingly, there are findings that are more easy to detect, like normal findings, 91%, effusion, 91%. Consolidation seems to be somewhat more complicated, only in the 70s, edema in the 80s, cardiomegaly in the 80s, and pneumothorax just below 80% in this study. This is another approach where they use different trained networks trying to aim for multiple abnormalities. These are how they set the curriculum for the learning, and then they are heat mapping the abnormalities with different colors, like the pneumothorax, the effusion, the consolidation, the nodules, the cardiomegaly. And here you can see that, again, the results are realistic. They trained it in a way that the sensitivity here is much higher. All the sensitivities are high in the 90s, but at the same time, the specificities are a little lower than in the other publication. So again, when you compare this to readers or to expert readers, this will be in the same range of our everyday performance. This is also new data presented at RSNA last year from the group in Seoul, where they compared radiologists using the deep learning algorithms or not using it. And you see that these algorithms, they are based on deep learning. They will improve the reading by the radiologist for nodules, effusion, edema, pneumothorax, and at the same time, reading time is going down. So this is what Paul mentioned. Workflow is the issue. If it's integrated, your results will be at least as good, probably even better, and you can get to this result faster. So we are moving from chest X-ray to CT. Obviously, chest CT is a very well-taken goal for these algorithms, as we have already seen in session 1. And you see that there are quite a number of activities going on looking at the detection of pulmonary nodules using AI tools. So we have the training data set with known diagnosis. So all of these nodules, they have to have histological proof. So this is the training data. Then the model is built and the learning algorithm is implemented. And then we are looking at a different data set and trying to predict these nodules, false positive, true positive, malignant. Not everything is perfect. There's error feedback. And so the whole system is, and an area under the curve of 87% in the prediction of benign or malignant nodules is really an exceptional result. And there are several publications out there. This is based on pulmonary nodules from the Large Lung Image Database Consortium, and the accuracy was 85% here, better than lung rats, which is the ACR promoted proposal to grade the risk of a nodule of being malignant. You can nicely see this is the how you can classify the groups of benign and malignant nodules. This is same number of nodules from a retrospective analysis of clinical routine CT, with very similar results. Accuracy 84%, sensitivity 93%, specificity 73%. And these are the different features, and they mapped out for the different histologies. This is a group from Oxford where they compared their tool with the simple nodule diameter. You know that size is one of the major predictors of benign versus malignant nodules. The Brock model, which is a risk model, and then you see the system. You see with the risk model, you can already improve the performance in your prediction of benign or malignant nodules, and using the AI tool, you can still improve this result. And this 92% is really a very good result. And this was the replication cohort. This is an EU-funded project where we compared these two nodules from different cohorts from Heidelberg, from Oxford, and from Groningen, more than 2,000 nodules. And again, all sites showed an overall performance of 92%. So again, something that a radiologist might not achieve on a routine basis. So we already heard about radionomics or radiogenomics, so not only predicting the nodule as being benign or malignant, but trying to predict the prognosis or trying to predict the somatic status of the cancer. So what you will actually do, you do the imaging, the segmentation, you extract all the feature that you will also learn for the use for the deep learning algorithm, and then you analyze, you present the data in a way how genetic data is presented. And then you can really have these heat maps, cluster maps of the clinical risk factors, the radiomic risk factors, and the genomic risk factors, and then you can use these to build upon each other to really predict not only whether it's malignant or benign, but also the histology and the prognosis. And what I already alluded to, you can use this to predict these somatic mutations. You know that these somatic mutations are currently very, very important, because then we could predict whether the certain very new immunotherapies will actually work or not work in advance. We are moving to airway disease. This is segmentation using some AI to really improve the segmentation results. And in this study here, they nicely showed that this is the conventional image processing of the airways. This is what they could actually achieve with the AI tools. So they are improving the visualization segmentation of the peripheral airways and almost are better than the gold standard. This is the manual annotation of the airways. You can also use this for emphysema. We've nicely seen that we're using the histogram, the density, the histogram, and then we can perform these cluster analysis to really describe the texture and the complexity of COPD and emphysema. And this is the holy grail in chest radiology, trying to segment and then characterize lung fibrosis, because this cannot be approached by a simple density-based approach. So you have to use these shape models, which are AI or based, or at least deep learning based, and you can use these shape models to really find which are fibrotic areas within the lung that you want to evaluate, and which is below the diaphragm or in the chest wall, what you don't want to evaluate in a quantitative way. And so you can very nicely see this is a well-trained, refined, density-based approach, and this is the deep learning approach. And you see that you have significantly different results and also a significantly better prediction and quantitation of fibrosis in the lung. And you can use this for follow-up of lung fibrosis with the new therapies that are currently available. And in the academic field is one thing. There are many of these spin-off companies which have also decided to go for the lung with their products, looking at nodules, at emphysema, at airways, at trauma, fibrosis. So there are a lot of first approaches out there. So in summary, we heard about the big data challenge that we are all trying to address. And I think we have to make sure that we can turn the big data into smart data for us as a radiologist. We really have to take care about the quality and the variability of the input data and the annotations. I like the proposal from Paul with this huge data set from China. But we have to be clear that a data set and a AI algorithm that's trained in China might not work in Europe. Especially for pulmonary nodules, we already learned that there are different histological subtypes which will have different CT phenotypes, and so it is really something about the input and the variability that is used to build such a system. That's why we need validation, and we need continuously learning systems. And as I presented, I think AI software can be used as a concurrent reader or as a pre-read to prioritize your working list, for example. And we certainly would, in addition to what Paul said about the workflow, we will need a direct feed into structured quantitative reports. And the radiologist will undergo some disruptive change in his working environment. So we have to be the validator, the adjudicator, and the communicator of the interpretation of these quantitative results. And we still have to reserve our right to use our human intelligence for discriminatory decisions. For example, the discussion is an MDT board. Thank you very much.
Thank you very much. Thank you very much.